Hi, thanks for joining me today. I'm going to be proving a theorem from number theory. Now, this is a very commonly used theorem, but the proof is quite nice, so I thought I'd share it with you. Here's what we have. We want to prove that for all epsilon bigger than 0, there exists a positive constant c, such that for every positive integer m, we have that tau of m is less than or equal to c times m to the epsilon. So let's quickly digest what this is. Epsilon is a positive number, and we're going to think of epsilon to be a really, really small real number, so a positive real, so 0.00001, and so on. So given a really small positive epsilon, we want to prove that then there exists a c, and this c here will depend on epsilon, such that for every positive integer m, we have tau of m is less than or equal to c times m to the epsilon. And tau of m is simply the number of divisors of m. Okay, so if you want to have a go at trying to prove this theorem, pause the video now and give it a go for yourself. And I'm going to get stuck straight into a proof. Okay, so the first thing we're going to consider is an arbitrary positive integer m, and then write it in its prime decomposition form. So it's p1 to the e1 times p2 to the e2 times so on, all the way up to pk to the ek. Well, here each of these pi's are just distinct prime numbers, and these ei's are going to be non-negative integers, or we can insist that they're strictly positive as well to ignore any kind of degenerate cases. Anyway, m is going to have this form here, and then what we want to do is show that tau of m is less than or equal to c times m to the epsilon. Well, another way of writing that is, or another, an equivalent problem is just saying that tau of m divided by m to the epsilon is bounded above by a constant c. So we're going to consider this quantity here, tau of m divided by m to the epsilon. And we want to show that this guy here is bounded above. So what is tau of m divided by m to the epsilon? Well, tau of m is in fact just going to be the product from I equals 1 to k of ei plus 1. Okay, so if you've not seen this result before, that tau of m equals this thing here, I've made a quick YouTube short video about it, so I'll leave a link for that in the description below. But essentially this comes from the fact that if we want to find a divisor of of m, then we have e1 plus 1 choices for the product for the exponent of p1 in that factor. We have e2 plus 1 choices for the exponent of p2 in that factor, and so on. And that's how we get the ei plus 1s. So that's what tau of m is, and m to the epsilon, well, m is just this guy here. So it's the product from I equals 1 to k of pi to the ei, all raised to the epsilon, like so. But we can write this in a kind of nicer form. This is just the product from I equals 1 to k of ei plus 1, all divided by pi to the ei epsilon, like so. So we want to show now that this guy here is bounded above. And now I guess one thing we notice is that if pi, which is a prime number, if it's really, really, really big, then this denominator here is going to be bigger than the numerator, which means the denominator being bigger than the numerator means it's going to be something that's less than or equal to 1, which is really good for us because we want to bound this above. So if we're multiplying something by a quantity that's less than 1, that's only going to help us. It's only going to make it smaller and not bigger. So that's great. So we only really need to worry about when pi is a small prime. So when pi is, when the denominator here is bigger than the numerator. To put that mathematically, notice that if pi is bigger than 2 to the 1 over epsilon, then pi to the ei epsilon, this guy here is going to be bigger than, or I could actually put bigger than or equal to, doesn't really matter, I'll leave it as bigger than, pi to the ei epsilon is just going to be bigger than 2 to the ei, but then 2 to the ei is going to be bigger than or equal to ei plus 1, like so. And yeah, you can prove this in a bunch of ways if you want to. You can do this by induction on ei, because remember ei is a non-negative integer. So look at the case where ei is 0. On the left-hand side we have 1, right-hand side we have 1, and then this guy here is going to grow a lot quicker than this guy. So you can prove by induction. You can prove it by, I think, Bernoulli's inequality. You can prove it by writing 2 as 1 plus 1, raising that to the ei, and then using the binomial expansion. There's a bunch of ways you can prove that, pretty standard though. So if pi is big enough, then the denominator here, pi e to the ei epsilon, is going to be bigger than the numerator, so it's going to contribute something that's less than or equal to 1, so we don't have to worry about those. We only need to worry about when pi is small, so pi is less than or equal to 2 to the 1 over epsilon. So all of a sudden this product is now going to be less than or equal to the product over the pi's being less than or equal to 2 to the 1 over epsilon of ei plus 1 all over pi to the ei epsilon, like so. And now this guy here we want to bound again. Well, notice that pi is a prime. Regardless of what I is, pi is always a prime, so that means it's going to have to be at least 2. So that means that 1 over pi is going to be at most a half, 1 over 2. So we can bound this straight away by the product of pi being less than or equal to 2 to the 1 over epsilon of ei plus 1 all over 2 to the ei epsilon, like so. So we now have that tau of m over m to the epsilon is bounded by this guy here, and we still want to bound this guy, show that it's bounded above by a constant. Well, if we just consider, if I wrap this off, if you consider another function, h of x, so this is from the reals, or from the non-negative reals to the reals, and it's going to be h of x equals x plus 1 all over 2 to the x epsilon. So it's essentially this guy here, but I've replaced the ei's with x. Well, what do we notice about this function? Firstly, it's continuous. It's nice and continuous, which is great. But also, if we look at the limit as x goes to infinity of this guy here, so take x to infinity in this guy here, this thing's going to tend to 0. Because although the numerator tends to infinity, the denominator does too, and the denominator is kind of going to infinity at an exponential rate, whereas the numerator is just a linear rate. So this, if you wanted to be a bit more rigorous or just convince yourself a bit more, you can just use L'Hopital's rule. But if you take x to infinity, this guy here is going to tend to 0. And what's nice about that is, if we draw the graph of h of x, when x is 0, it's going to be 1 over 1, so just 1. And we don't know really what it's going to do. It might go up and down a bit, not really sure. But in the end, it's going to tend towards 0. Okay? And what's quite nice about that, it means that because it's also continuous, it's going to be bounded. Okay? So any continuous function that has a limit, the limit doesn't have to be 0. Any continuous function that has a limit is bounded. So that means that this guy here, we don't know what it is, but we'll call this, say, c tilde. There exists some c tilde such that h of x is less than or equal to c tilde for all x. And if you want, you can go ahead and compute it by differentiating this, setting it equal to 0, but we don't actually need to, we just need to know that a c tilde exists. So this guy here is certainly going to be less than or equal to c tilde. So this is going to be less than or equal to the product pi being less than or equal to 2 to the 1 over epsilon of c tilde, like so. Now, in the case that c tilde is less than 1, less than or equal to 1, well, then we're kind of done, because if c tilde is less than or equal to 1, then we're just multiplying 1 or something that's less than 1 a bunch of times, so then it's going to be less than or equal to 1, which solves our problem, so just setting c equals 1 will do. But if c tilde is bigger than 1, well, this thing here is just going to be equal to c tilde to the, let's call it x, say, and x here is just the number of pi's less than 2 to the 1 over epsilon. Well, we can certainly bound x. X is certainly going to be less than or equal to 2 to the 1 over epsilon, because the number of primes less than 2 to the 1 over epsilon must be less than or equal to 2 to the 1 over epsilon. If you want to know how many primes are less than 100, it's certainly going to be less than 100 primes. Yeah, obviously. So this thing here is going to be less than or equal to c tilde to the 2 to the 1 over epsilon. This is a really crude, silly upper bound, but it's an upper bound, and it's independent of what m is, and so we can just set c equals this guy here, and that solves our problem. So, yeah, that solves our problem. Tau of m divided by m to the epsilon is bounded above, so that gives us this guy here. Now, of course, this constant here does depend on epsilon. Sadly, we can't find that there's no universal bound independent of epsilon, but what's quite nice about this is it shows that the number of factors of m grows really slowly. It grows more slowly. It grows more slower than any power of m, which is quite cool. Anyway, thank you for watching. I hope you have enjoyed this video. I'll catch you in the next one. Have a great day.